Welcome back everyone to our second video here. As I promised, we need some practice actually applying this thing, the mean value theorem. So we're going to practice once through at least what happens if your graph is given to you graphically, or your function is given to you graphically. What happens if your function is given to you via an equation? And that's kind of our bread and butter, that's the standard stuff. And again, we want to reemphasize that the mean value theorem doesn't apply to all functions. But every once in a while, right, it doesn't apply. So we do have to be careful here. All right, let's get started then. In our first example, you can see that I have not given you the equation for this function, right? So all we have is a graph, and we would like to at least be able to estimate a c value that satisfies the conclusion of the mean value theorem on the interval from 1 to 4. So here's our 1, here is our 4. Remember, we're on this interval between 1 and 4. This is our region that we're staring at. You can kind of forget about the rest of the graph to some extent. And remember that the mean value theorem says that there's somewhere where the tangent line is parallel to the secant line. Well, that means that maybe a good first step, let's go ahead and draw out our secant line. So here's our secant line between the endpoints. Of course, the line, it goes on forever. Something like this. All right, but there is our secant line between our endpoints there. And our goal is to find a c value where the tangent line at that c value is parallel to this secant line. So, okay, if I was going maybe too fast or something like this, I may say like this one right here. If I was to draw the tangent line through this point, you would see and you'd say, okay, yeah, that looks parallel to the secant line. So maybe the value for c should be something like 0.5 or something like this. That maybe this would be a good c value. But again, remember that it needs to be between this 1 and this 4, that we are not on the interval. So actually this does not work for a c value, right? So we have to ignore this one. The correct one that we don't want to ignore is somewhere over here, somewhere right around 3-ish. Right? And if I go ahead and I draw my tangent line at around 3, we can see that it's parallel to this secant line. So somewhere right around 3, there's a good c value where this is parallel to the secant line. So I'm going to go ahead and say c is equal to 3. Now, without more information, without the equation or anything like this, again, this is really just an approximation. We have to do kind of the best that we can. It's around 3, but maybe it's 3.1 or something like this. But again, we can still test, do you understand the statement of the mean value theorem with a graph? Okay, now let's kind of get into our kind of more standard problems where we have an equation given to us for the function. So I'd like to go ahead and do the second example here. So with all of these, right, again, the mean value theorem does not apply to every single function out there. So we really have to back up, and I'm going to ask, can the mean value theorem be applied to this function on the interval 0 to 1? If yes, find a c value that satisfies the conclusion of the mean value theorem. If no, explain why not. So I'd like you to take 2 minutes, pause the video, kind of, you know the drill probably. You may need to go back and look at the statement of the mean value theorem again, but take 2 minutes, try to get as far as you can on this, and then I'll spoil the surprise. All right, and the claim is the answer is yes in this case. So remember, in order for the mean value theorem to apply, it needs to be continuous. Well, this is a nice polynomial. It's continuous everywhere. So continuous, check. In particular, right, again, it's continuous everywhere, so it'll be continuous on any interval that you choose, let alone this one, 0 to 1. And then differentiable. So for differentiable, well, let's go ahead and calculate out the derivative. So I'm going to do f prime of x is equal to 2x plus 3. And okay, is there anywhere where this doesn't make sense, where it doesn't give out a real number answer? And the answer is no, right? So there's nowhere that you're dividing by 0. There's nowhere that you're taking the square root of a negative, anything like this. So this is differentiable everywhere, especially on this interval from 0 to 1. So it is continuous, it is differentiable all on this interval. So it satisfies the hypotheses of the mean value theorem, so we can go ahead and apply it. So again, the mean value theorem says that there's somewhere where the tangent line is parallel to the secant line. So we're going to do the secant line f of b minus f of a over b minus a. Again, remember, here is our a value, here is our b value. Those are given to us by the interval there. So I'm going to do f of b minus f of a over b minus a. So let's see, if I plug in 1, I'll have 1 plus 3 plus 5, so that should be 9. F of 0, so if I plug in 0, I'll have 0 plus 0 plus 5, so that'll be 5. And then 1 minus 0 will just be 1 in this case. All right, so our average rate of change is 4. Okay, so that's the slope of the secant line. And again, we should have the slope of the tangent line being equal to this if we want them being parallel to each other. So there's some value out there where the slope of the tangent line, aka the derivative, is equal to the slope of the secant line. In this case, we calculated it out. It was 4. So if I go ahead and rearrange, I'm going to get 2x is equal to 1. And so I get x is equal to 1/2. And so this is the correct c value. Usually I would change this and maybe make it a c equals 1/2. This is the correct c value where the slope of the tangent line is the same as the slope of the secant line, right? If I was to take this 1/2 and if I was to plug it back in to our derivative, aka our slope, right, I would get 2 times 1/2, that'd be 1, plus 3 is also 4, right? So both of them are 4, they have the same slope, so they're parallel to each other. Notice that this 1/2 value, it is in the interval from 0 to 1, right? So it needs to be between 0 and 1. In this case, it certainly is. But maybe sometimes you solve and you get 2 values and you need to exclude one of them maybe if it's not in the interval. Okay, there's our first example. Kind of a relatively nice example. They kind of get more difficult from here, so let's do this one right here. Our function is now 1 over x. Again, the question is, can the mean value theorem be applied on the interval from 1 to 3? If yes, go ahead and find a c value. If no, explain why not. You know the drill. Take 2 minutes, get as far as you can, right? Pause the video, and then I'll spoil the surprise. Okay, and the surprising answer is yes in this case. You may think it is no because, right, you can see you can divide by 0 here, right, and then it wouldn't be continuous. But the claim is that it is continuous on this interval, right? So the only place where it's not continuous is at x equals 0. So at x equals 0, this is not continuous. However, the interval doesn't include 0. So in fact, this is continuous on that interval from 1 to 3. Now the question is about differentiability, right? Is it differentiable? Well, let's go ahead and take the derivative. F prime of x is equal to, and you may have done this so many times now that you're just writing down -1 over x squared, but let's review where this comes from, right? So this is the same thing as x to the -1st power, right? Because this is x to the first, so you can raise that up. Okay, and now if I wanted to take the derivative of this, I would apply the power rule, right? So that -1 would come down, that's giving you this, and then you'd get x to the -2nd power. So x to the -2nd power, well, you can make that a positive exponent by pushing this into the denominator. So that's where that comes from. Okay, so there is our derivative, and we want to know, is it differentiable on the interval from 1 to 3? Well, again, you can see it's not differentiable at 0, right? If you were trying to plug in 0, you'd be dividing by 0. It wouldn't make any sense, right? You wouldn't get out a real number answer. But in this case, thank goodness again that 0 is not in our interval, so it is differentiable, right? Any of the values, 1, 2, 3, anything between those, 1.5, so on and so forth, right? They all make sense in the derivative function. So yes, it's going to be differentiable on all of these things. So it's continuous, it's differentiable, so we can apply the mean value theorem. Okay, so let's go ahead and calculate out then the average rate of change, right? We want our f of b, in this case 3, minus f of 1 over 3 minus 1. Again, we're getting our a's and our b's from here. And we're now calculating out this average rate of change. So f of 3, that's going to be, well, I'm plugging in 3 everywhere I see an x, so that's 1/3. Let's see, 1 over 1 will be 1, and then 3 minus 1 will be 2. 1/3 minus 1, so that should be -2/3. And when I divide that by 2, that should give me -1/3. So there is our average rate of change, and we want to find a c value, right, where the slope of the tangent line is the same as the slope of the secant line, aka negative 1/3. So let's go ahead and set these equal to each other. Negative 1 over x squared is equal to negative 1 over 3. Let's do a nice little cross multiplying here. So I would get negative 3 is equal to negative x third. X squared. And I can go ahead and divide by this negative sign on both sides, right? Kind of getting rid of these. That's very nice. And now in order to solve for x, I could take the square root on both sides. Remember, when you apply a square root, you have to do the plus and the minus. So this is going to be plus and minus root 3. But again, remember that we are on this interval from 1 to 3. We want a c value that's in this interval. So we're not going to include the negative, right? So the negative root 3 is, well, less than 1 certainly. So it's not in this interval. Remember, root 3 itself is around like 1.7-ish. So in this case, our only c value is c equals root 3. And that would be my final answer. But again, with all of this algebra here, you sometimes lose track of what on earth we're doing, right? So I want to go ahead and maybe bring this back to what on earth we're doing with a graph. So I went ahead and I graphed some stuff here. Let me scroll up. So this is our function 1 over x. So here's our function 1 over x. And we're on this interval from 1 to 3. You can see it's nice and continuous and differentiable on this interval here. And then I went ahead and I graphed the secant line. So there's the secant line between these two endpoints, the one at 1 and the one at 3. So there's our secant line. Again, we want to find a place where the tangent line is parallel to the secant line. So if I go ahead and I throw in my tangent line, and you can see I made a little slider here so we can kind of move this around. And if we were playing this game, I'd say somewhere right around in here-ish. This looks pretty good, right? So this is a place where the tangent line is parallel to the secant line. So this would be my c value around 1.764. Now in reality, we just solved and we saw that our c value should actually be the square root of 3. And so the square root of 3 is actually a little bit off from that, right? It's 1.73205, so on and so forth. But now you can see that this is now perfect. It's perfectly parallel. Even as you zoom out and stuff, you can see that they never cross each other. So that's what all that algebra did for us. We found, using algebra, the correct c value for where the tangent line is parallel to the secant line. All right, we have one more example to go through. Consider the function with the absolute value, right? F of x is equal to the absolute value of x, and I want to know, can the mean value theorem be applied on the interval from negative 2 to 2? If yes, you know the drill, right? It's a standard question that we've done a couple times now. Pause the video, take 2 minutes, get as far as you can, and then I'll spoil the surprise. All right, you may have guessed it. In this case, we finally have a no, right? So the mean value theorem cannot be applied for the absolute value function on the interval from negative 2 to 2. And so if I was to go ahead and sketch it out, right, so here is my nice absolute value function. And maybe from negative 2 to 2, so something like this. Well, you can notice that it is continuous on this interval, right? The absolute value is continuous. I could draw this picture without lifting up my pencil at all. But we have a problem with differentiability. Right, so it is not differentiable here at 0, and it turns out that's a big deal, right? So one of the conditions for the mean value theorem is that it needs to be continuous from negative 2 to 2, and it needs to be differentiable from negative 2 to 2, I guess not including those points. So the answer, no. Explain why not. So absolute value of x is not differentiable at x equals 0. And I'll just say which is in the interval from negative 2 to 2. So this is a big problem. In this case, it will turn out that the mean value theorem, you can't find such a c value. And if you were to try anyway, maybe you forgot that sometimes the mean value theorem doesn't work, right? And if I was to go ahead and maybe draw in my secant line, you notice that both of these have the same height. They're at height 2 at these endpoints. So you're trying to figure out a place where the tangent line has slope 0, right? Because the secant line has slope 0. We want these things to be parallel, so the slopes should be equal to one another. So where does this function have slope 0? And the answer is nowhere, right? So if you look over here, this is a nice straight line. It has slope -1. If you're over here to the right of 0, this has slope 1. And then again, remember, at 0, the derivative, aka the slope, right, is undefined. Or does not exist, right? So undefined. So there's none of these places, whether you're less than 0, bigger than 0, or equal to 0, none of them have a derivative, or the slope of the tangent line, being equal to 0. So again, this does not apply. Okay, so that is the mean value theorem. I see we've got now plenty of practice. We'll do some more in class, but there's a strange consequence that comes along with this mean value theorem. So I have one more video. It's just one more page, really. Something that comes up because of the mean value theorem, and this becomes very useful later in chapter 3. So 3.9 will be using this a lot, and also chapter 4. So I'm going to go over a strange consequence of the mean value theorem in one more video. I'll see you guys then.